Okay, can everyone see and hear me?
I can see and I can hear.
Okay, perfect. All right, so the last unit is on the derivatives of special functions. So we're going to learn how to derive 6 of those today, tomorrow, and Wednesday. So we're starting off with today learning to find the derivative, slope of the tangent to functions of the form y equals e to the g at x, so e to some function of x, which is an exponential function with a base of e. E is a number, so we know pi is a special number. The number e is also special. It's named after Swiss mathematician Leonhard Euler, who was alive between 1707 and 1783. Pi and e are both irrational numbers. So if you can, find the e to the x button on your calculator. Now I have a graphing calculator, so mine is, see this ln, which is what you're going to learn about this afternoon, natural logarithm. It's my second to that. So I go second e to the, and if I just put e to the power of 1, it'll give me the approximate value of e, which is 2.718281828. See if you can locate that button on your calculator and use it to find e to the 1. I know there's lots of different calculators out there. Sometimes you have to put the 1 first and then hit your e button. Some it's your e first and then the exponent. Okay, so that's what e is approximately, but it's irrational, so the decimal goes on and on forever, never repeats, never stops. And we'll look at calculus is actually why e is such a special number. So consider the function f at x equals b to the x. Okay, so where b is a number, so that's an exponential function, if you remember from advanced functions. So in advanced functions, you probably looked at functions like y equals 2 to the x, y equals 3 to the x, y equals a half to the x, etc. So according to the definition of the derivative, first principles formula, f prime at x is the limit as h approaches 0 of f at x plus h minus f at x over h. So if this is f at x plus h would be, so I'm going to replace x with x plus h, b to the x plus h. So if I come down to my first principles formula, f prime at x is going to be the limit as h approaches 0 of, so I'm going to replace f at x plus h with b to the x plus h minus f at x is just b to the x. So I can replace f at x with b to the x over h. And if you look at these scoops here, there actually is a common factor, and that common factor is b to the x. I'll show you here on a piece of paper. So if I take b to the x plus h and mentally divide it, but I'm going to just show you the actual division here, and divide it by b to the x, the common factor. I'm dividing powers with the same base, so I keep the base and subtract the exponents. So x plus h minus x is just b to the h. So b to the x plus h divided by b to the x is b to the h. B to the x divided by itself is 1, and I still have that over h. So I can't let h approach 0. There's no way for me to get rid of that problematic h yet. But I do see that this b to the x doesn't depend on h. So as h approaches 0, it doesn't affect b to the x, so I can move it out front of the limit. So b to the x times the limit as h approaches 0 of b to the h minus 1 over h. And then we're going to think about what does this actually represent? The limit as h approaches 0 of b to the h minus 1 over h. And you'll see that it represents something cool. So just what is this? So our first principles formula for finding the slope of the tangent of any function at x is this formula. Our first principles formula for finding the slope of the tangent at a specific point was f prime at a equals the limit as h approaches 0 of f at a plus h minus f at a over h, where a is the number that you're finding the slope of the tangent at. And it turns out that if we find f prime at 0, basing it on our function being the same function f at x equals b to the x, so f at 0 plus h is just f at h minus f at 0 over h. So f at h, well, if f at x is b to the x, can you see it back up there? Yeah, you can. So if f at x is b to the x, then f at plane h would be b to the h. So f at h is b to the h minus f at 0, according to our function, f at 0 is b to the exponent 0. But we know that any number variable to the exponent 0 is 1. So f at 0 is 1 over h, which you can see is exactly what we have in this red box over here. So when our function is f at x equals b to the x, this limit here represents f prime at 0, or the derivative of the function at x equals 0. So f prime at x turns out to be b to the x times f prime at 0. So that's the derivative. Now what's going to happen is, depending on what b is, f prime at 0 is always going to change. It's going to be something different depending on whether the base is 2, 3, 4, 5, 6, a half, 4. So I've written down at the bottom here that as the base b changes, so does the value of f prime at 0. For a very fortunate base, somewhere along the way, f prime at 0 will turn out to be 1. And it follows that if f prime at x is b to the x times 1, the derivative is also b to the x for that very special base, which is very cool. And I'm going to prove to you that that very special base is e, and that's why e is so special. So we can investigate and find out what that base is, where the limit, where f prime at 0 is the limit as h approaches 0 of b to the h minus 1 over h. We're going to try different bases. Different values of b are different bases. And we can't use h equals 0, obviously. We want it to approach 0, so we're going to, like you hopefully did in advanced functions, we're going to choose our h to be 0.0001. So when you do this calculation in your calculator, so I'm using the base as being 1. So if I'm doing this, I'm letting h approach 0 by letting h be 0.0001. So I'm doing 1 to the exponent 0.0001. I know 1 to the anything is 1. Yep. Minus 1 is 0, divided by 0.0001 is still 0. Now I'm going to try a base of 2. So on my calculator, I'm doing 2 to the exponent 0.0001 equals. Then I'm going to subtract 1 equals. And then I'm going to divide by 0.0001. And I get 0.69317. And remember, I want to get 1. I want f prime at 0 to end up being 1. Because then the derivative is just e to the x for that fortunate base. So now we're going to try the base being 2.5. So 2.5 to the exponent 0.0001 equals minus 1 equals divided by 0.0001. We're getting closer to 1, 0.91633. Now I'm going to try the base 2.6 to the exponent 0.0001 is minus 1 equals divided by 0.0001, 0.9555. Getting closer to 1. Try the base 2.7. Subtract 1 equals divided by 0.0001, 0.9933. 2.71 we're going to try as our base next. Oops, minus 1 divided by 0.0001, 0.996998. Very close to 1. 2.718 to the exponent 0.0001 minus 1 divided by 0.0001, 0.999946. Very close to 1. And then we're going to try 2.8. We get 1.02967. So that very special base has to be between 2.718 and 2.8. Somewhere in between here, we're going to get our base where f prime at 0 turns out to be exactly 1. It's exactly 1 when b is equal to Euler's number E. Okay? So if you do that, so try find your e to the button, e to the 0.0001 minus 1 divided by 0.0001. It's 1.000502, but that's because we used an approximation for h. Okay? So the special base is e, and that means when f at x is equal to e to the power of x, then f prime at x is also e to the power of x. So that's cool. When the function is e to the x, its derivative is also e to the x. And that's again because the derivative of b to the x is b to the x times f prime at 0, but when the base is e, f prime at 0 is 1. And applying the chain rule, when f at x is equal to e to the g at x, so e to some function of x, then f prime at x is e to the g at x again. So that's the outer derivative. And then multiplied by whatever the derivative of the exponent is, g prime at x. So this would be the outer derivative. And this would be the inner derivative. So that means if we were deriving y equals e to the x squared. Y prime, the outer derivative, is e to the x squared back. And then the inner derivative multiplied by the derivative of the exponent, which is 2x. So that would be y prime, e to the x squared times 2x. That's the chain rule. Okay, so that's our kind of our setup. Now we're going to practice finding derivatives. So our first question, 1, f at x is equal to e to the 2x, determine the derivative. So f prime at x, the outer derivative is going to be e to the 2x back, and then multiplied by the derivative of the exponent. Derivative of 2x is 2. And then you can write that nicer as f prime at x equals 2e to the 2x. Any questions for that one? Okay. So for b, y is equal to e to the x squared minus 3x. So y prime, or dy by dx, your choice, is going to be e to the x squared minus 3x. And then that's the outer derivative, times the inner derivative, which is the derivative of x squared minus 3x, which is 2x minus 3. And that one doesn't really have a simpler look to it. Either the textbook will have it look like this, or it will have the 2x minus 3 in brackets first, one or the other, depending on the textbook. For C, we've got y equals x squared times e to the x. So what would we have to use in order to find the derivative?
Product rule.
Product rule, good. We have two functions of x multiplying together. So we have to use the product rule. So we're going to make our chart here. So our first function is x squared. And our second function is e to the x. And the derivative of x squared is 2x, using the power rule. And the derivative of e to the x is just e to the x from today. So y prime is going to be derivative of the first times the second, plus the first times the derivative of the second. And then we can put this one into simplified factored form. So what's the common factor among the scoops?
X e to x e to the x.
Yes, x e to the x, very good. So if I divide the first scoop by x e to the x, I just get 2 left. And if I divide the second scoop by x e to the x, I just get x left. So y prime is x e to the x times 2 plus x. And there it is in simplified factored form. Okay, d h at x equals e to the 3x divided by x squared. So now I have a quotient rule to use. So I'm going to make my chart. First, second, function, derivative. So my first function is e to the 3x. My second is x squared. Derivative of e to the 3x, so the outer derivative is e to the 3x, and the inner derivative is the derivative of 3x, which is just 3. And you'd want to write that as 3e to the 3x. And the derivative of x squared is 2x. So that means h prime at x is going to be derivative of the first times the second, so 3e to the 3x. Oh, sorry, I wouldn't write it like that, my bad. I'd probably do the 3x squared and then the exponential part. So 3x squared e to the 3x minus 2x e to the 3x over x squared squared. That's just applying the quotient rule. And then again, I want to look and see if I've got a common factor amongst the terms in the numerator. Three and two, no, just one's in common. X squared and x is in common, and e to the 3x is in common. And then if I divide 3x squared e to the 3x by x e to the 3x, I'm going to get 3x minus 2 over x to the 4th. Does anyone see anything else I could do?
Subtract the x.
Yeah, so I have powers with the same base dividing here. So this would be x to the negative 3 if it was in the numerator, but I know that that's going to be x cubed in the denominator. So there's my solution in simplified factored form. Awesome. Okay, so now we've got f at x is equal to the square root of x times e to the x. So I know that that's the product rule, but I'm going to first rewrite root of x as x to the 1/2. Make my chart. So x to the 1/2 is my first, and e to the x is my second. 1/2 x to the negative half, and just e to the x again. And it's the product rule. So f prime at x is going to be derivative of the first times the second. Plus the first times the derivative of the second. And then I'm looking at these. Does anyone think they know the common factor?
X to the negative 1/2.
That's part of it. Anything else?
And EX.
E to the x, good. And I'm going to force the half out as well. So if I divide the first scoop by the common factor, they're exactly the same. So I just get 1 plus, so I'm going to get a piece of blank paper here. When I'm dividing the second scoop, remember there's really a 1 invisible 1 in front of there, by 1/2 x to the negative half e to the x. What's 1 divided by 1/2, or how many times does 1/2 go into 1? Twice? 1 divided by 1/2 is 2. Everybody good there?
Yep.
No? 1 divided by 1/2?
Oh, I said yep.
You said yep, okay. Just in case, that's 1 divided by 1/2. If you use the multiply by the reciprocal, you get 2. So 1 divided by 1/2 is 2, so there's my 2. X to the 1/2 divided by x to the negative 1/2 is just x. And then the e to the x's divide out. And then to finish it and make it look prettier, I'm going to keep the e to the x and the 1 plus 2x factor in the numerator, and the 2, and I'm going to change x to the negative 1/2 to 2 root x in the denominator here. And there it is in simplified factored form.
Miss Northwood,
Yep.
I'm wondering if it's a pattern where the I guess the two numbers that are multiplying the e to the x, whatever term that is, it's the exponents from the original function of the two numbers. Like for this one, like for d, for example, we had 3x minus 2 multiplying there, and that's the exponents from our original equation.
And here we had 1/2 and x.
Yeah. I suppose if you hadn't factored out the 1/2.
Oh, I see it. I see. Yeah. I don't know. It looks like it could be.
Yeah. There you go.
All right. For f, we've got the function y equals, in brackets, 1 plus 5e to the negative 10x all to the 4th. Any ideas about how you would go about finding the derivative? It's not product rule. It's not quotient rule. It's chain rule.
Chain rule.
Yes. So the 4 times 1 plus 5e to the negative 10x cubed. There's my outer derivative. This is going to be like a chain rule with a bunch of links in it. Inner derivative, derivative of what's inside. The derivative of 1 is 0. The derivative of 5e to the negative 10x is going to be 5e to the negative 10x. But then I also have to multiply that by the derivative of the exponent. And then just to make it look a bit nicer, I can multiply the 4, the 5, and the negative 10, and the e to the negative 10x and put that out front. So that's going to be negative 200 e to the negative 10x times 1 plus 5e to the negative 10x cubed. And kind of my rule for E is if there's a negative exponent in the question, then you can leave your answer with a negative exponent in the answer. Similar with if it's the question has a radical, then your answer should have in radical form. Okay, G, y equals 3x squared times e to the 2x. That's a product rule question. So we can make our chart. So our first function is 3x squared, and our second function is e to the 2x. We need the derivative of each of those. The derivative of 3x squared is 6x. And the derivative of e to the 2x is e to the 2x times 2, but I would write that as 2e to the 2x. So y prime is going to be the derivative of the first times the second. Plus, so if I'm multiplying 3x squared by the 2, that's going to give me 6x squared. E to the 2x. And then I'm looking for a common factor. So 6 is in common, x is in common, e to the 2x is in common. And that's going to give us 1 plus x. Agreed?
Agreed.
Agreed? Okay. On to the next one. All right, determine the slope of the tangent to the curve y equals 3e to the x squared at the point where x equals -1. Okay, so it's a slope of the tangent question. So we want to find the derivative and then substitute -1 in for x. And this is a fairly straightforward one. So if y equals 3e to the x squared, it's just our normal e chain rule. So it's going to be 3e to the x squared multiplied by the derivative of the exponent, which is 2x, which we could write as 6x e to the x squared. And we want to know y prime at 1.
Isn't it at -1?
Sorry, thanks, John, at -1. So y prime at -1 is going to be -6, and then e, because -1 squared is 1, so -6e. And rather than giving an approximate decimal, you want to keep it in terms of e, just like when you're working with radians, you keep things in terms of pi. And then you need your therefore. M tangent is equal to -6e. All right, now we've got one we're applying to yesterday's stuff, implicit differentiation. Find dy by dx if x e to the y plus 6x squared y equals 0. Any suggestions? So if we just look at the first term here, does everyone see that that would be a product rule, a function of x times a function of y? So we need one chart here. So our first is x, and our second is e to the y. And the derivative of x is 1. Anyone want to take a stab at the derivative of e to the y?
dy over dx times e to the y.
Very good. E to the y times dy by dx. So the outer derivative is e to the y times the derivative of the exponent, derivative of y with respect to x. Awesome. And then, so we can start off doing that. So we've got our e to the y. I'm going to actually write this in a color. So the derivative of this is going to be written in orange. E to the y plus x e to the y dy by dx. And then the 6x squared y is also a product rule. The first function is 6x squared, and the second one is y. Derivative of 6x squared is 12x, and derivative of y is dy by dx. And I'll do that part in green. So it's going to be plus 12xy plus 6x squared dy by dx equals 0. So now I'm going to keep the terms that have dy by dx on the left side and subtract e to the y on both sides. And subtract 12xy on both sides. Common factor out dy by dx. Divide both sides by x e to the y plus 6x squared. So therefore dy by dx is negative e to the y minus 12xy over x e to the y plus 6x squared. Someone's not muted. I can hear myself through your microphone. Thanks. Okay, so that's an implicit example. Any questions about that one? Okay, so our last one's a word problem. So the number of bacteria in a culture at time t and hours is given by the function number at time t is equal to 2,000, and then in brackets 30 plus te to the negative t over 20. Okay, so t is time in hours, and n is number of bacteria. So A says find the number of bacteria in the culture at t equals 10 hours. So remember, that's not asking for a rate of change. It's just asking for the number. So it just wants n at 10. So this is where we got to make sure we can use our calculator. So we can give an exact answer, but we can also give an approximate number, which for a word problem, we normally want an approximate one. If I want an exact one, I might multiply the 2,000 through here. So it's going to be 60,000 plus 20,000 e to the negative half. Which I could write, I don't know, prettily as exactly. I don't know how pretty it is, but this would be exact. I could write e to the negative 1/2 as over the root of e. But I want you also to be able to just enter this into your calculator. So I'm going to go back to just this first step here and enter that into my calculator. So I'm going to do inside the brackets first. So 30 plus 10 times my e button, and then open a bracket, e to the, I can type in negative 10 over 20, even though I know it's negative 1/2 if I want to. Negative 10 divided by 20, closing bracket, equals, so that's what's inside the brackets, and then multiply by 2,000. And I get n at 10 is approximately 72,130, I guess I could round to the nearest bacteria, 31 bacteria. So make sure you can get that in your calculator using your E button. If you're trying to put the last piece in your calculator here, I would probably do 2,000 divided by the square root of e to the 1 for that part, and then press equals, and then add 60,000. Uh-oh, I got a different answer. Did I make a mistake somewhere? Oh, it was 20,000. That's what I did wrong. I would do 20,000 divided by the square root of e to the 1, and then add 60,000. There we go, same number. Okay. Right, and then part B says, at what rate is the culture growing? So now we're doing a rate, so we know that we're talking about the derivative, and it's exactly at t equals 10 hours, so it's not an average rate, it's an instantaneous rate, which means I need to find n prime at t. So I'm going to start off just with n at t. And I want to make it as easy on myself to find the derivative as possible. So similar to when we were doing the optimization questions, I'm going to expand that first, because I know when I take the derivative of 60,000, it's just going to be 0. So 2,000 times 30 is 60,000. And then 2,000 times t e to the negative t over 20. So when I find n prime at t, the derivative of 60,000 is just 0. And the derivative of this part, well, we need to make a chart. We have 2,000t being multiplied by e to the negative t over 20. So two functions of t multiplying together, so that needs the product rule. So our first function is 2,000t, and our second function is e to the negative t over 20. So the derivative of 2,000t is just 2,000. The derivative of e to the negative t over 20. This gets people sometimes. So e to the negative t over 20. But what's the derivative of negative t over 20? Get a piece of paper. So I could rewrite negative t over 20 as negative 1/20th t. And what would be the derivative of that? Just using the power rule, it would be 1 times negative 1/20th, t to the 0. So just it's negative 1/20th. Convince yourself of that. So the derivative of the exponent is just negative 1/20th. And then I'd probably write that as negative 1/20th e to the negative t over 20. So now I want to use the product rule. Derivative of the first times the second. So 2,000 e to the negative t over 20. And then notice here, when you multiply the coefficients, 2,000 times negative 1 over 20, you're going to get negative 100. So I'm going to multiply the coefficients and I get negative 100. I've still got the t, and then I've still got the e to the negative t over 20. Now I could just sub 10 in right now, or I can put it in simplified factored form if I want, and then sub 10 in, whatever I prefer. I might as well just factor it because it doesn't look too hard. I know 100 is part of my common factor, and the e to the negative t over 20 is 2,000 divided by 100 is 20 minus t. And we want n prime at 10. So that's going to be 100 times e to the negative 1/2 times 10. Or 1,000 e to the negative 1/2. And then you've got to be able to put that in your calculator. So find your e button, open up a bracket, or you could just put to the negative 0.5. So e to the negative 1/2, just that part should be 0.6065306. And then multiply that by 1,000. And you get 606.5. So n prime at 10 is approximately 606.5. And then it's a rate, so it's got to have units. So it's going to be bacteria per hour. And then I need a therefore statement because it's a word problem. So therefore, the culture is growing at a rate of 606.5 bacteria per hour when T equals 10 hours. So finish that statement, and then I want to go back to the first page. I forgot to just talk about the graph of that exponential function at the very beginning. So I'd like to do that before you try the practice. That's a typical word problem, rate of change again, except for this time we're applying our special function e. I just wanted to go back. I forgot to talk about the graph here. So this is the graph of y equals e to the x. And remember from advanced functions, that's what exponential functions look like. They always go through this point 0, 1, unless there's any transformations. And they always have a horizontal asymptote along y equals 0. And they grow exponentially. And this afternoon, you'll be looking at the inverse, which will be a logarithmic function, the natural log, which is also, it's got a really cool derivative. I think you'll really like it. Okay, so I'm going to stop recording and go back. Stop recording.